Hello and welcome to our presentation. In this project, we did a survey of image-to-image translation methods using deep learning, and now we're going to talk about some of them. We'll start with neural style transfer, then we'll move on to pix-to-pix, then we'll do CycleGans, and finally we'll do CoCosNet. All right, let's start.
So, the traditional approach of neural style transfer was first introduced by Leon Gattis in 2015 in his paper A Neural Algorithm of Artistic Style. It aimed to utilize deep neural networks, more specifically convolutional ones, to simulate the complex interplay between content and style of artistic paintings. To accomplish this, a separate style and content loss has to be computed and optimized. Next slide. Neural style transfer has a number of interesting applications. Besides the original aim to gain a better understanding of how humans create and perceive art, neural style transfer has also gained traction as a tool for training purposes of other deep networks. Gyros used the style transfer technique to reduce the bias of an image classification model towards texture in a paper in 2018. However, it has to be noted that ADA-in was used here rather than an iterative approach as proposed by Gattis. Also, style transfer is a highly relevant theme for photo and video editing. Next slide. So first, let us have a look at the full model setup. In our implementation, VGG19 is used, but the setup is very similar. We have a respective style and content target and minimize the corresponding losses through the pre-trained layers of the VGGNet. These are picked to be convolutional layers before pooling. As mentioned before, to create the generated image, loss with respect to the style and the content target has to be minimized. In order to do so, one must first consider the content loss. Next slide. So the content loss can be derived from the feature maps of the layers of the convolutional neural networks. Intuitively, layers at the beginning, so the high layers of the model, are more sensitive to the content of the image. The content loss is then given through the Euclidean distance between these intermediate features at the high level. Representation of input image X and content image P for the specified layer L. Next slide. The style loss, however, is more complex, as it's not simply recognized through singular high feature maps. To measure it, the Gram matrix was used. It represents the full distribution of features in a certain layer and is obtained by acquiring the correlation of a matrix with its transposed form. This is the key of retrieving style rather than content, as the feature layers themselves can represent a certain aspect of the content, such as edges or textures, but only in combination with each other can they represent a certain style pattern. To acquire the loss, we take the distance of the Gram matrices of the newly generated image and our style source image. The contribution of a style information layer is thus given by the first equation shown here, and in turn, loss over all layers altogether comes out to the second equation, where W_L denotes the factor layer L contributes to the full style loss. Next slide. To speed up the training process and yield better results, some optimization measures are taken. Firstly, the losses are multiplied with certain weights to make up the total loss. In our case, we are working with 0.1 for the style and 1000 for the content. It is worth to note that a higher value is needed for the content in order to maintain the original content picture. Another step taken to better the final result is a decrease on the high frequency artifacts, as to prevent too much noise in the picture. This is also called reducing the total variation loss. In order to include it in the optimization, we assign a weight of 30 to it and include it in the total loss parameter. This will help the image to appear less noisy and preserve the content edges in the final generated image. That's it from my side, and now we continue with pix-to-pix.
Another paper that has received a lot of attention is one called Image-to-Image Translation with Conditional Adversarial Networks by Philip Isola and others. The paper includes a method called pix-to-pix, which is very obvious reference to the main of operation, which is image-to-image translation. It utilizes an extension or alteration of generative adversarial networks that doesn't just take noise at input, but also an input image, of which the aim is to translate it from its own distribution into another. This is what gives it the conditional name, since given the condition of one image, we can output another image related to this condition. Next slide. In a standard general adversarial network, we take a vector of noise, which is this, in this slide is denoted Z, and aim to map it to an output Y. In Pix2Pix, we also use this noise to avoid deterministic behavior, risking only to map the delta function. But this may in fact not be needed, as there are other methods to avoid this, like for example, with the use of dropout, which the Pix2Pix paper actually found to be more effective. It is worth noting, however, that the results using this method is not very stochastic. In other words, the output look very similar given the same inputs. But this problem is still very much left open to improvements in present work. Before we talk about the loss function, let me explain the decision behind using general adversarial networks in the first place. If you think about the task of translating an image into another, doesn't it seem natural to use a convolutional neural network? It does, but the problem is the loss function. How do you specify one that makes the output look realistic and not blurry? It turns out to be very difficult, and hence general adversarial networks seem to be a good alternative, as there we strive to match the distribution. And if this is a realistic distribution, thus the loss function practically becomes make the images look realistic. We hence use a formulation very similar to the standard GAN loss, but with the inclusion of L1 regularization. This was empirically found to generate better results than L2, and general best practices with GANs is to mix one of these traditional loss regularizations. As you can see in G star, the discriminator's job remains unchanged, and it tries to maximize the loss, while the generator tries to minimize with the parameterized L1 loss added. Next slide. In this slide, we wanted to clarify more schematically how the process of training looks. So to the left, we have a diagram showing how the generator receives the edges of a shoe from which it tries to synthesize an image of a real shoe. The pair of the generated shoe and the input is given to the generator, and it's then given to the discriminator as a pair, which it tries to classify if the two match or not. In the diagram to the left, you can see that the shoe has been generated, and thus hopefully the discriminator identifies that this is fake, and we can backpropagate such that both entities learn. Next slide. The generator is a unit where the first part aims to understand what is in the image by downsampling with convolutional layers. The second part of the model tries to understand where things are located in the upsampling process. The middle part of the generator forms a bottleneck where the input information is the most dense. In order for this bottleneck not to discard low-level information that could be useful, skip connections are added. Each skip connection simply concatenates all channels at layer I with those at layer n-i. For many image translation problems, there is a great deal of low-level information shared between input and output, and would be desirable to shuttle this information directly across the net. For example, in the case of image colorization, the input and output share the location of prominent edges. Next slide. The discriminator of Pix2Pix is known as patch GAN, and as the name hints, it is related to patches. The discriminator method only considers n times n patch of the full input, and only for one particular patch at a time it aims to classify if it's real or fake. The motivation behind this is because a smaller discriminator has fewer parameters, which speed up the computational time, and the technique is also applicable to images of arbitrary sizes. But the question remains, what size of the patch is optimal? In the paper, experiments show that around 70 times 70 seems to be an efficient size. A smaller size can lead to blurriness and repetitiveness, as can be seen in the lower image. Next slide. Before moving on from Pix2Pix, let's actually see some example of what it can do. Here are some applications presented in the original paper. The results in this paper suggest that the conditional adversarial networks are a very promising approach for many image-to-image translation tasks, especially those involving highly structured graphical outputs, as these networks learn a loss adapted to the task and data at hand. It makes them applicable in a wide range of settings. Next slide.
All right, and now we'll look at CycleGANs and contrastive learning. These are methods for unpaired image-to-image translation, so the data doesn't need to be paired beforehand. And CycleGANs can be seen as an extension of the pix-to-pix in that they use the same discriminator and generator. Contrastive learning GANs are an alternative method to CycleGANs that is generally quicker to train. And we'll first look at the CycleGANs. So as before, we have a source domain and a target domain, and each domain has a generator and a discriminator. With the generator, we want to generate images that have distributions g of x that are indistinguishable from y. But just because a distribution is indistinguishable with our measure doesn't mean it's actually meaningful to our eyes. Because as we have seen in the lectures, just because an image has the same distribution as another image doesn't mean it actually means something to our eyes. So the point here is that we need to add some constraint to this. And that's where the cycle consistency constraints come in. We introduce a new mapping, which is a generator, f, that goes from the target to the source instead, and the corresponding discriminator. And the goal is for our model to be able to go in a circle. So if we start with an image from the source, and we make it to an image to the target, and then go back again, we want the images that are, we want the original image and the returning image to be very similar. So as you can see in the picture there, you go from the source to the target and then back again, and we want those to be close to each other. Mathematically, we formulate this as first the regular adversarial loss that we had before, and this is for each pair of generator discriminator. And then the cycle consistency loss is just the difference between the original picture and the picture that has gone the full circle in the model. And we do this for images from both the source and the target domain. We then mash everything together to get the total loss. So that's a quick overview of the model. Some applications we can see here. They perform quite well on this kind of translation, where the content is similar, but the style is what's changed. We implemented our own CycleGAN, which did the satellite to maps for 10 epochs. As we can see, the results require a lot more training, but because training is quite slow, we didn't really have time for that. And training with CycleGANs is slow, as I said, so that's where we also looked at another method, which is contrastive learning. The fundamental problem is the same, but the approach is different. Here we try to maximize the mutual information between corresponding input and output patches. So we take for an input image and an output image, we take a patch that's the same, and then we take a bunch of random patches on the input image, and we want the corresponding patches to have kind of the same look. And mathematically, we formulate it as this. We have a query, which is the patch on the output image. We have a positive example, which is the corresponding patch on the input, and then a bunch of negative examples, which are the random patches. And the loss is just a simple classification problem. It represents the probability of the positive example being chosen over all the negative as the one corresponding to the query. So we use logits and the cross entropy loss, and we get the following loss, as you can see in the slide. And then we do this for many different layers of the encoder. So we select L layers and SL patches for each layer, and we calculate the loss from all of this. We also input the patches through a network, but that's you can read about that in the report. So we basically get the losses from a bunch of different patches from a bunch of different layers, and this is our full patch loss. We combine this with adversarial loss to create the full objective. So some comparison between these two methods is that, well, first of all, they both give good results for image-to-image translation, and both methods do not require any paired training data, which is good because it reduces the work required to implement these models. However, contrastive learning trains faster, mainly because it does not need the cycle consistency loss, and therefore only has one generator and one discriminator. And this, of course, requires less computations. All right, now we'll move on.
Finally, a last example of image-to-image method is example-based image-to-image translation. It's a user-flexible approach to generate new images from cross-domain input images. We've seen the principle earlier, but I remind it. It's similar to style transfer, except for the fact that here, the spatial structure of one of the two input images is mixed with the other input's image, similar parts, to generate a new image that respects both of these properties. It can be a post-body application where we generate an image of someone in a specific input pose. Next slide. Or it can also be an edge-to-face application where we impose, for example, new expressions and angles to an input face. Next slide. The purpose of the CoCosNet version 2, which is a full resolution correspondence learning approach, is to be generic. So it was designed as an amelioration of the CoCosNet version 1, which render in poorer quality translations. Its orbital architecture is split into 3 parts: domain alignment, patch matched, and translation. So next slide. Let's first dive into multi-level domain alignment. Next slide. As the input images domains are different, we first need to extract features from both these domains in order to be able to compare them with similarity metrics. In CoCosNet V2, this is done by learning a mapping function for each domain to then build a finite number of latent spaces for both input images, which range from low to high qualities, to high resolution, sorry. Once it's done, features are extracted through a unit architecture such as the one presented in Pix2Pix approach. Then the next part is to find, next slide. The next part is to find correspondence in the images. This is done by using patch match. Next slide. Patch match is an algorithm to find the correspondence based on the neighborhoods and not the global search, with 3 steps: random initialization, propagation, and random search. For our problem, the analysis consists of running patch match on the extracted features. Next slide. In the GRU assisted approach adopted in this paper, convolutional gated recurrent units based refinement is performed after the propagation step. Previous layers results are used for the next layer's initialization step by upsampling. In the classical patch match version, propagation is the process of exploring neighbors which can be trapped into local optimants. By using these GRU-based refinements, selected distant candidates are investigated instead of the randomly searching for them in the neighborhood. This refinement should act also as a correlation of the incorrectly matched patches. Next slide. Finally, the obtained warp exemplar image are combined through a translation network, which uses spatially adaptive denormalization, also called SPADE. Next slide. To do so, concatenation of warped image is performed in the channel dimension with upsampling if needed. This concatenation is then projected through 2 convolutional layers to produce parameters alpha and beta for style modulation, and then output image is generated by forwarding through the translation network. Next slide. So all of these steps result in an approach which provides better quality images with improved semantic consistency and more style relevance than other state-of-the-art methods. You can see like an example in the next slide. Sorry, next slide. You can see an example by comparing with SPADE and CoCosNet version 1. Next slide. To conclude this image-to-image deep learning, sorry, next slide. No, it's okay. Sorry. To conclude this image-to-image deep learning method survey, we have briefly explained 4 different methods for 4 different applications. As you can see, this is a very broad field where each and every application requires different techniques and architectures. So we hope that this serves you as a guide to give you an intuition about how complex applications are performed and what to choose for your project. Thank you.